Okay, so note 6.6 is the properties of definite integrals. So if we look at the first example, we are given the graph of f of x. And on number 1, it wants us to find the integral from 0 to 12 of f of x dx. So we're finding the area between the x-axis and the curve from 0 to 12. So I'm going to go ahead and highlight that. So that's this area of a half circle, this area of a trapezoid, and then the area of a triangle. Okay. Now I'm going to use that space that's right above the title. You guys should have a decent amount of space there. Okay, so starting with the semicircle, we know that the area is equal to pi r squared divided by 2. What is the radius of that half circle? 2. So this is pi times 2 squared over 2, which gives us 2 pi. Okay, so the area of that semicircle is 2 pi. Okay. Then we have the area of the trapezoid, which is area is equal to 1/2 h times base 1 plus base 2. What's the height of the trapezoid? 2. Okay. What is the small base of the trapezoid? 1, and then the large base? Okay, so 1 plus 4. That gives us 5 because the 1/2 and the 2 cancel out. And then we have the triangle, which is the area is equal to 1/2 base times height. What is the base of the triangle? 4. And what's the height? 2. So it's 1/2 times 4 times 2, which gives us 4. And since this triangle is on the other side of that x-axis, is it going to be a positive or negative area? Negative. So I write negative 4. Okay. So for number 1, since I'm looking at the area from 0 to 12, I'm just going to add all these areas together. So I have 2 pi plus 5 minus 4, which gives me 2 pi plus 1. Okay, 2 pi plus 1. So that's the answer to that integral. Okay. Looking at number 2, what is different from number 1? Good, it goes 12 to 0. And remember, when we're looking at our integral, it's always the start value to the stop value. So technically, our lower bound should be smaller. Okay. So what this is telling us, if we were to take this whole graph and flip it upside down, okay, all of our positive areas are now negative, and all our negative areas are now positive. So I'm going to do that. This is negative 2 pi minus 5 plus 4, which gives me negative 2 pi minus 1. So you can make a note that this is the graph is flipped upside down. So now we're going to look at some properties of the definite integral. So looking at the first one, we have equivalent limits. So this is the integral from a to a of f of x dx. That means we started at position A and we stopped at position A. So did we go anywhere? No. So with this property, if our bounds are the same, then we say 0. Okay. Almost like when we were talking about that other property, that if we had one positive and one negative, if you were to add those areas together, we would also get 0. Okay. Number 2, where we said we took the graph and we flipped it upside down, so everything turned negative, that is actually called the reversal of limits. So if we want to switch the bounds, that's the same as just making the integral negative. Okay. which if we look back at number 1, we could have just took the answer 2 pi plus 1 and made each of the terms negative. So 2 pi to negative 2 pi, 1 to negative 1, without having to recalculate the area. Okay. The next property is the multiply by constant. So if the function is being multiplied by a constant, in this case k, we can actually remove k and put it outside of the integral. So we can do k times the integral of a to b. What? There we go. A to b, f of x dx. Okay. The next property is the adjacent interval. So if we look at these two integrals here, we have the integral from a to c plus the integral from c to b. So notice on these bounds, on the diagonal, those two bounds are the same. So the upper bound of the first and the lower bound of the second. Okay, they're the same. This is the same as us saying, okay, I'm going to take my graph, my diagram, and divide it into two areas and then add those areas together. When instead, we could just look at the total area of the entire graph and say that this is the integral from a to b, f of x dx. Okay, and of course, that is assuming c is in between the bounds a and b. Okay, so that's like saying I have the integral from 0 to 1 and then 1 to 2. Well, that's the same as just saying the integral from 0 to 2. Okay. The next two are the addition and subtraction property, which states that if we are adding or subtracting two functions, we can actually rewrite this as two separate integrals. So this could be the integral from a to b of f of x dx plus the integral of a to b g of x dx. Okay. Same with the subtraction. We can take that one single integral and separate it into two integrals. So integral to a to b f of x dx minus integral a to b g of x dx. Okay, so these properties are some of the basic ones that we're going to learn and practice in these notes. Yes?
Can you explain the multiply by constant one again? Because, like, isn't it like the same thing? Or does it mean k? Or, like, just can you explain it?
It's just if we are having, like, let's say this was 3x. So instead of saying the integral of 3x, we could say 3 times the integral of x. You could just bring the 3 on the outside. It doesn't seem like that big a deal for that small of equation, but imagine you had a super long equation where you could easily take out a GCF, and that GCF could be placed outside. Okay, so notice in this graph, it's the same graph that we did on 1 and 2. So we already know the areas for each of these. So what was the area of the semicircle? 2 pi. What about the trapezoid? 5. And then the triangle? -4. Okay, so we already know all those areas from the question 1 and 2. So number 3 says, what is the integral from 7 to 6 f of x dx? Okay, so first, is this the integral from our lowest to highest? Or is it backwards? It's backwards. So based off the properties, we know that we can rewrite this as what? Negative. Go ahead and say it.
6 to 7.
Integral from 6 to 7 f of x dx. So we rewrote it using our properties. Okay. Now we can go look at our graph and actually see where the area they want us to find. Okay, so color coding it on 3. I'm looking at 6 to 7. That is this area here. And since these are 1 by 1 boxes, I can simply say that the area of that box is 2, but since the integral is negative, our answer is negative 2. Okay, yes?
Why didn't you use the universal limits here?
Because our lower bound should always be our smaller number. So looking at number 4, we can actually use 2 properties. What's the first one?
The multiply by constant.
Okay, multiply by constant, which means we can remove the 3 and put it on the outside. And what's the other one?
The reversal limit.
Good, reversal. So we have 12 to 8. What should it really be? 8 to 12. So this is equal to negative 3. So negative because of the reversal, 3 because we're taking out that constant of the integral to 8 to 12 f of x dx. So I go on my graph and I look at from 8 to 12, okay, which is this entire triangle here. Okay, so then I take negative 3 times negative 4, because that's the area of the triangle, and I get what as my answer? 12. See, are you guys having fun yet? Yeah, I mean,
Party Mix now playing on Spotify.
whose phone was that? That was my phone? What? What? Oh my gosh. Party mix. That was random. Okay. Too bad it didn't play my most recent song. It was Excavator by Blippi. You know, I'm an excavator. No, okay. That's what my kids are obsessed with, Blippi, right now. Okay. Let's go back. Okay, so the next couple questions, they're giving us 3 integrals. And then from these 3 integrals, we're going to have to use the properties and solve the other integrals given. So, for example, we are given the integral from negative 2 to 1 of f of x, from 1 to 5 of f of x, and then from negative 2 to 1 of g of x. So in part A, it wants us to find the integral from 5 to 1 f of x dx, which means the first thing we should do is what? Flip it. So then that makes the integral
3.
Okay, yes, you're skipping a step though. From 1 to 5. It makes it negative. Right, it's the notes. I want to make sure it's all step by step so you guys can go watch it later. So yes, since we flipped it, we made it negative, and our original one from integral 1 to 5 is already a negative 3. So negative times a negative 3 gives us a positive 3. Okay, looking at B, it says the integral from negative 2 to 5. Do we have that integral out of our 3? Not exactly, but what 2 can we combine? Negative 2 and 1 of which one? Because remember, we have 2 of those. F of x. So we can say that this is the same as saying negative integral of negative 2 to 1 f of x dx plus the integral from 1 to 5 f of x dx. Okay? Because if we combine that, since on the diagonal, they're both 1s on those bounds, if we combine that, we get our total interval. So that is going to be 4 plus a negative 3, which is 1. Okay, so the next one, part C, we have 2 properties. What are those properties?
Negative 2 to 1 f of x. So then it would be
Good, so the addition property and multiply by constant. So this is actually the integral from -2 to 1 f of x dx plus 2 integral -2 1 g of x dx. So then I find the integrals that they already gave us. So that is going to be 4. So this is 4 plus 2 times 8, which is 20. Okay, what about d, the integral from 0 to 1 f of x dx? Do we have any integrals that we could use to solve that? No, we do not. So we say it can't be determined. That doesn't mean it can't be solved. We're just not given the information to solve it. Okay, for example, we're not given what f of x is. We're only supposed to use those 3 integrals to find out what these other answers are. Okay, go ahead and take a minute and do E and F. Combined should take you less than a minute because you guys are that good and it's that easy. Okay, so group 7, what's the answer to E? -12, perfect. Group 8, what's the answer to F? 0, perfect, thank you. So here,
It says g of x for -2 to 1.
okay, so we're going to swap this to make sure we have our lower bound in the correct spot. So we make this a negative integral to -2 to 1, 3. Well, I could have done this in one step, but I'm writing it in 2. 3 f of x dx, and then take out the 3. So this is -3 integral -2 to 1 f of x dx. That means this is -3 times 4, which is -12. For f, did we have to do any math here? No. How'd you know it was 0? Good. It starts and stops at the same number. So if you start and stop at the same position, do you go any distance? No. So it's 0. Any questions on number 5?
Why could D not be determined?
D can't be determined because we're not given enough information. So for example, if we look at all the integrals given for f, we have -2 to 1 and we have 1 to 5. There's no property that says that we could use the middle ones. Not yet. Okay. So now we're going to look at piecewise functions and then integrals of an absolute value function. So number 6 is the function g is defined by g of x is equal to 3 for x less than 2 and 4 minus x for x greater than or equal to 2. So it says, what is the value of the integral 1 to 5 g of x dx? So the first thing we need to do is graph this piecewise function. Okay, so it says 3 for x less than 2. Is that going to be an open dot or a closed dot? Open dot because it is less than. So let's see, 3, 2, so it's going to be right here. And we're only going towards the x value smaller than 2. And then we have to graph 4 minus x, which is just a linear function. So we can think of it as -x plus 4, which is going to be here to here. Okay. So once we graph the piecewise function, we're going to highlight the area that they want us to find. And they want us to find 1 to 5. So that's this whole space and then this little space down here. So even though we have a jump right here at 2, we are still going to use the space between the jump as part of our area. Okay, so for example, I'm going to be looking at the entire area of this rectangle. Okay, the entire area of this triangle and the entire area of this little triangle. Okay, and I'm going to add them all together to find what my integral is. So, looking at just that rectangle first, since these are 1 by 1 squares, we know that area is 3. Okay, then looking at the triangle, we know that area is 2, so plus 2. And then that little tiny triangle at the bottom, 1/2. Okay, would we say plus 1/2 or minus 1/2? Minus, so minus 0.5, which means I get the answer of 4.5. Okay, so the main idea here is that we include the area between the jump. Okay, now let's look at number 7. Number 7 says, what is the value of the integral 0 to 5 of the absolute value function x minus 2 dx? So first we graph that absolute value function. Okay. Once we graph the absolute value function, we want the area from 0 to 5. So that's this little triangle here, and then this larger triangle here. Okay. So again, since we're assuming these are 1 by 1 boxes, what would be the area of that first triangle? 2. So this is 2 plus, and then the area of the larger triangle? 4.5. Okay, because look, here's 1, 2, 3. These 2 half are 4, and then this half is 4.5. Okay, and then that gives us the answer of 6.5. Okay, notice we didn't have any negative areas. Why? Good, nothing's under that x-axis because this is what type of function? Absolute value. When you take the absolute value of something, it's always positive. Okay, any questions on 6 or 7? You guys are the only class that laugh at that. You know that, right? Just you guys. Just you guys. Maybe that's so. You guys are the smartest, so you have like that intellectual ability to laugh more. I don't know. Okay, next concept. Okay, so now we're given a new graph, and they want us to find the difference between taking the absolute value of the integral and taking an integral of an absolute value. So first, looking at this, we're going to go ahead and we see that both of these are the integral from -2 to 4. So I'm going to go ahead and shade those areas. Okay, so we have 2 half circles and a triangle. Okay, now we're going to calculate the area for each of these. So half circle is pi r squared divided by 2. What is the radius for each of these circles? 1. So that means the first area for that first half circle is going to be negative pi halves, right? Because it's below the x-axis. The other one is going to be pi halves because it's above the x-axis. And then looking at our triangle, what is the area? 2. Okay, so now we're looking at number 8 where it says the absolute value of the integral. That means we are going to literally take the absolute value after we add these all together. So this is going to be negative pi halves plus pi halves plus 2. So the absolute value of that entire thing. What's going to happen to the pi halves? Cancel. So I'm left with the absolute value of 2, which is 2. Versus number 9, where it's saying they want us to look at this function here and take its absolute value. Well, we know when we take the absolute value, do we have any negative areas? No, so we're going to redraw this circle, that half circle that has the negative area, and we're going to draw it to be a positive one. Okay, so this is now positive pi halves. Okay, so we're getting rid of all of our negative part of our area and making them positive. Okay, so now when we add them together, we have pi halves plus 2, which gives us, good, pi plus 2 or 2 plus pi. Okay, are these answers the same? No, so if we had to compare taking the absolute value of the entire integral or just the function, which one is greater? Just the function. So we just proved this right here, that the absolute value of the integral is less than or equal to the absolute value, of the integral of the absolute value function. Mouthful. Okay. This is an important concept. I would highlight it, star it, box it, especially on multiple choice questions.
Is that true for like all problems like that?
Yes. All problems, no matter the function. Okay. So again, we say less than or equal to because these could be equal to if, let's say, our original function consisted of all positive areas. That means we're not changing any areas to make it positive. They're already all positive. Okay. Any questions? Okay, last concept here, Desmos. Okay, so I'm going to go ahead and pull up Desmos. Okay, so for this one, it wants you to sketch the graph and then define the integral using a calculator. So in our case, Desmos. So first, in order to make that sketch, let's say you forgot how all the functions look like. Okay, so just write your function in there, square root of x minus 1. Okay, so it looks like it's going off of 1 and then in the positive direction. Oops. Okay, and our integral here wants us to look from 2 to 3. So this whole space right here. Okay. Well, since we have access to Desmos, I can go ahead and go to Functions, scroll down to Statistics, click on the integral, and then put in the bounds. So from 2 to 3. Then I'm going to write my function. So again, the square root of x minus 1. And what do I have to remember to always include? Dx, because notice it doesn't give me an answer unless I put dx. Okay, so dx, and then I get what as my answer? Good. I'm just going to round it to 3 decimal places. So 1.219. Okay, which makes sense because if I was to zoom in on that shaded area that I'm supposed to be figuring out there, I know it's going to be greater than 1. I just don't know what this little area is going to be here. Okay, but again, we had access to a calculator so we could find the exact value. Okay, we're going to do the same thing for number 11. Okay, number 11. Let's say I don't remember what x over 3 minus 1 looks like. We should, right? Because it's a linear equation. Let's say you're having a rough day. You don't remember. Okay. Here's what the graph looks like. Okay, it looks like it's crossing through -1 and 3. Okay, our linear equation there. And then we are looking at the area from -2 to 4. So it's that triangle and then this little tiny triangle up there. Then I go back to Desmos, I go to functions, scroll down to calculus, click on the integral, and I'm going to do from -2 to 4. And then my function, x divided by 3, bless you, minus 1, and then dx. And what's my answer? -4. So this actually gave me an answer that was exact, meaning I probably could have calculated this based on the area of those two triangles on my graph.